All right, significant figures, as we just went over in the PowerPoint, these are basically used to show how accurate a value is. So for example, if we have a number, suppose you were like using a scale or something, and you saw that it weighed, whatever object you put on there was 36,724. The readout read that number, and this is in grams. So the way that these numbers work on any kind of digital readout is the first few digits there are known with good accuracy. So these numbers right there, everything but the 4, those are considered to be the certain values. So they are certain. Actually, let me zoom in a little on the doc. There we go. Focus. There, that's good. All right, and so these are the certain values. So those are what the instrument knows with a good amount of accuracy. Go ahead.
Will this be on the PowerPoints later or not?
I'm recording right now, so I'm actually just going to include it on there. So, all right. So here we have the certain values. The last value here is the one that if you've ever used a digital scale before, you may notice that last digit kind of jumps around a little bit. And that's because the instrument's trying its best to estimate what it is. So this is estimated. And it's always the last digit on any kind of digital readout. And it's not just for scales, any kind of digital readout. That's part of the reason why they add the extra digit in gas prices, is to account for uncertainty in the measurements of the volume that's being transferred. And they don't want that uncertainty to be in a whole cent amount, because then people are going to complain. If it's like fluctuating up and down to be like 5 cents, 10 cents, people are going to complain. But if it's fluctuating as a fraction of a cent, no one really seems to care all that much. On that note, there's actually really strict laws on that, because there are issues with people basically getting to the higher end of the cent and basically skimming off the top by a rounding issue that no one's even paying attention to. But the way to measure people is pay attention to that. So, for example, if you go to another thing on these lines, like weird laws that we have in place for a good reason. If you go to, like, say, the meat department in a grocery store, and you go there and they put, say, that piece of paper up there, and then they put your steak up there, if they didn't tear the weight first, they're technically breaking the law. Because what they're doing is they're charging you for the weight of that paper. So I usually call them out on that, because depending on what you're buying, that could add up to $1 on there, depending on what you're buying. All right, so moving along here. So this is when you're looking at a digital readout. The thing is, with working in the lab, you don't always have a digital readout available. So some methods have an uncertainty built in, others are estimated. My wife's telling me to get a GoPro and I can just wear it on my head, and then it can just record whatever I see. But I don't want to post you guys in the video, so because I'm sure I'm going to look up at some point and see you guys. All right, so when measuring manually, the last digit is estimated. Or I like to say guesstimated. So this is the case of what you're going to have to do when you're working with, say, like a ruler or a graduated cylinder, anything you're doing manually. You need to make sure that you estimate out one extra digit. So the example I want to give here is, like, imagine we have a ruler, and let's go ahead and say it's measuring in centimeters. And suppose we are looking at a point, say, after 1 centimeter, and then we're going to go between 1 centimeter and 2 centimeters. And I want to put a few notches in here, so let's go ahead and say that this notch right here, the ruler reads to be 1.5. So 1.1, 1.2, 1.3, 1.4, and then 1.6, 0.7, 0.8, 0.9. All right. So this particular ruler measures accurately up to 1 decimal place. The thing is, though, when you report your answer, or whatever measurement you're making, you have to report to 2 decimal places because you have to make sure you include the certain values as well as the uncertain values. So, for example, suppose you were measuring an object and say it went out to, let's just say over to here. How do you guys think you should report that value? So you're thinking like 1.6. So, well, 1.9 would be way out over here. So these are like, this is a 1.6, 1.7, 1.8, etc. to 2. Yep, so we know for certain it is 1.6. That's your certain values. And what comes next is based off what your eyes are seeing. So you and your classmate might see slightly different values, and that's the equivalent of that number jumping up and down on the digital readout. Is basically 2 different sets of eyes seeing slightly different values. I usually just estimate to be 0.5 or 0.05 if it's somewhere in the middle. And then if you think it's closer to one side or over the other, you can just lower or raise that number as you see fit. What do you guys think about what if the value landed right, what you thought to be right on a line? So right there. Yep, so you need to report this. So we know for certain it's probably about 1.2. And then you need to add the extra digit on there so that you're thinking it's landing right on the line, but that's still an estimation. It might actually be like a hair off one way or the other. So you have to make sure that you include that extra digit on there. Don't say that it's just 1.2. It is 1 extra digit. And these would be centimeter, right? Because numbers are meaningless without units. Okay. Are there any questions about how we identify significant figures by measurements? All right, so this is actually a twofold thing. Since we aren't actually doing a lab in this class, you're going to be doing most of your Sig Fig identification by looking at numbers that are written for you already. Like someone else measured these. And what you're going to have to figure out is what numbers do we even worry about Sig Figs with, and how do we deal with them in calculations. And then later on, when you guys get into your other lab classes, you'll have to consider all these rules on top of how we actually measure them accurately. And then your lab instructor will go over that. That's actually the lab they're doing this week in Chemistry 121, is how to use a ruler and graduate a cylinder and all that fun stuff. All right, so what I'm going to go ahead and go over now is counting Sig Figs. Go this way. Counting. You guys probably guessed we do like to call them Sig Figs for short. And then we'll go ahead and go over some examples here. I want to go ahead and just give you all the rules though up front. All right, so the first rule for counting Sig Figs when you're reading a number is all non-zeros are significant. And I'm just going to further abbreviate that to SF. That's typically, if you're missing something for significant figures on your test, that's typically what I'll write. So if I put an X or something and write SF, that does not mean that you have the answer wrong. It means that your Sig Figs are wrong. And I usually mark off, I put the X on the digits that are extra or you're missing something. So just be aware that I like to write SF there for short. All right, the second rule is that interior zeros are significant. So what that means basically is that you have zeros that are in between non-zeros. Those are considered to be significant. All right, and then number 3, trailing zeros to the right of a decimal are significant. So once again here, trailing zeros to the right of a decimal are significant figures. And then the next rule here is that leading zeros are, what do you guys think about leading zeros? They're not significant. They act as placeholders. All right. So let's go ahead and take a look at a few numbers. So basically, you're doing your homework problem. You have the numbers written out for you. How do we deal with them? So what if we have, let's go ahead and start with the simple one. I believe this one. So how many significant figures are in that number? So basically you count how many digits are considered to be significant. There are 4. So the 1 is a non-zero, and then we have all these zeros here. These are significant. So for FF, you're typically not going to be asked to identify the certain or the uncertainty values. We look at it collectively as they're all significant. Let's go ahead and take a look at another number. So 1,230 with no decimal. How many significant figures do you think we have there?
3.
There are 3. Yep. This one, this trailing zero is actually serving the same role a leading zero would, meaning it's just a placeholder. It's putting the first digit into the thousands place. So it's an order of magnitude thing. The cool thing about working with numbers this way is that when you work in scientific notation, what we just talked about earlier, the number in front in your scientific notation represents the number of sig figs that you have. So the way I would write this in scientific notation, I would not just write 1 times 10 to the 2. I would write it as 1.000 to make sure that this number also has 4 significant figures times 10 to the 2. And then this one here, I know my number has 3 sig figs, so I'm only going to have 3 digits when I put it into scientific notation. So 1.23 times 10 to the 3. This is a really great, I actually prefer scientific notations in a lot of cases, like the lower number here in particular. Some people think that last zero there can make it ambiguous or not, whether that last digit is significant or not. And the way you can be really clear about it is put it in scientific notation. Everything there is significant in that front digit. The way that we work with scientific notation and sig figs. All right, let's do a few more examples here. So this is 4, 0, 3, 2, 0. What do you guys think for that one? There are 4. So we have a few rules in play here. So we have the non-zeros, and then we have that interior 0, which is also significant. So if the 0 is trapped between non-zeros, then it is significant. So this one has 4 sig figs. So 4 FF. And then putting it into scientific notation, let's go ahead and write 4.032. 4 digits to make sure it matches with the number of sig figs. And then 10 to the what? 10 to the 4. Yep. Okay. Let's go ahead and do another example here. Make a number that's smaller now, just to illustrate some other points. And I want to clarify rule number 3 for you guys. All right, let's go with that one. What do you guys think? How many sig figs are in that number?
2. 6.
I still haven't heard the correct answer. 3. There are 3. Yep, there are 3 significant figures here. So what's happening here is the leading zeros are not significant. So they're acting as a placeholder. They're working the same way that this 0 and this 0 were. They're not part of the significant numbers. They're just pushing it to the correct order of magnitude. However, though, if you have a trailing 0 after a decimal, that 0 after the non-zeros here, that is significant. So I know there can be, it might seem a little ambiguous with rule number 3. So I think we should add there to the right of the decimal and non-zeros. So let's go ahead and add that in here. And non-zeros. Usually people don't add that little wording there in the rule though, so make sure you guys aren't messing up with that. So not only are you going to have to learn how to do calculations correctly, you have to make sure you're reporting your numbers correctly as well. So the extra layer that we add onto things in science. All right, so we agree that there are 3 Sig Figs. So I'm going to go ahead and put it into scientific notation now. And that way it's really clear how many Sig Figs there are. There are 3. So 4.20 times 10 to the 4? Negative 4. Yep. We went the other way now, so this number is smaller. So negative sign 4. All right. And we'll definitely see more examples of this with stuff that we're getting into here in a minute. But before we do that, are there any questions about these examples here? All right. I did mention to you guys last time that I am allowing a little cheat sheet on the quizzes we're going to be taking. I think I mentioned it anyway. I do allow cheat sheets. I do allow cheat sheets on everything except for the final exam. So your normal exams and your quizzes, you can use a cheat sheet, 3x5 note card. And I recommend for the first test to have your Sig Fig rules on there if you're having a hard time with it. Because this is usually, I know it seems really simple, but it's really easy to get lax in the rules and make small mistakes and then lose points because of it. All right, before we get into the portion about calculating, I want to mention here the time where we don't apply Sig Fig rules. And these are for exact numbers. So there are 3 different types of numbers that we're going to come across. 2 of them in particular in this class, but there are 3 different types where they are considered to have an infinite number of significant figures. So these have an infinite number of SF. And these are things such as a count of discrete objects. So count of objects. So for example, if I say that, I have 2 pens, would it make sense to say that I have 2.0 pens when I have exactly 2 pens in my hand? It does not make sense to say like extra decimals with that, does it? So we just say that number 2. That number 2 is considered to be an exact number because, like I said, I have exactly 2 that have an infinite number of significant figures in it. And you shouldn't specify exact after it either. You just say 2. Right. The next one is the one that gets students the most often, and these are defined quantities. I like to call this table information. Anytime you read a number that is either a definition, so these are things like your conversion factors, numbers off the periodic table, any charts that you may have in your textbook, whatever. These are considered to be defined quantities and exact numbers. What we're building up to here is that we're going to be doing calculations with numbers, and you have to consider how many Sig Figs are in each number when you do your calculations. If you have calculations that include one of these kinds of things here, then they're not going to limit the number of Sig Figs that are in your answer because they're defined values. All right, the last one, we don't see it too much in this class. You see it a little bit in Chem 122, and this is numbers that are part of an equation. So for example, if we're calculating, say, wasn't there an equation pi r squared? What is that, circumference? I'm trying to remember. Is that circumference? Pi r squared? Or that's not area, is it? What is that? Which one is it? Let's use the easier one. Area of a triangle is what? 1/2 times base times height?
Yeah.
So suppose you had a triangle, you wanted to measure the area for it. Which values in that would you measure? You'd probably measure the base and the height, right? Did you measure the 1/2? No. You did not measure that. It's part of the equation. It has an exact number. So in your calculation, if you're trying to limit your sig figs to make sure that you're representing the accuracy of your measurement, you don't limit it by the 1/2 because that number you did not measure. That was defined quantity, part of the equation. All right. So they said here the simplest thing I think with identifying sig figs, definitely be careful here with exact numbers. Like I said, that's where most people trip up on, is they limit their sig figs by exact numbers. But the main thing we're doing here is doing calculations with them. So there are technically 3 sets of rules that we use in chemistry for using sig figs and calculations. Only 2 of the rules though that we worry about in this class, and they're for the different mathematical operations. There's multiplication and division, addition and subtraction that we're going to use, and then later on when you guys get to chemistry 122, you will learn about the logarithm rules. Because they use logarithms in that class. We don't touch logarithm stuff at all in here, or in 121, I don't think. Just, a tab, but you do all the hard stuff in 122 with logarithms. All right, so first things first, the multiplication and division rules. The way this rule works out is your result carries the same number of significant figures as the factor with the least number of sig figs. And I'm going to try to make that as brief as possible, make the rule as simple as possible for you. So the result has the same number SF as the least. As the number with the least. All right. So let's go ahead and take a look at an example there. So we have what? 2.304 times 3.14. So I know the number is close to pi. I'm not actually using pi here. How many sig figs do you guys think pi has? Has an infinite number. We do know the value of pi up to a lot of digits, but honestly, pi is actually an exact value. It doesn't translate well into a base 10 number system. That's why I have all these weird digits at the end. All right, so I'm going to break out my scientific calculator. So here we have 2.304 times 3.14. All right, so what I like to do typically is I will go ahead and just do the calculation normally. So we have that 3.234, blah, blah, blah. But before I write it down on my paper here, I want to follow my sig fig rules. So first thing you want to do is identify how many are in each number. So what about this number here? There's 4. So let's use purple. Point at anybody. So we have 4 SF, and then the next one has 3, right? Yeah. 3 SF. How many digits do you think our answer should have? 3. So we look at the 2 that are involved. One of them has 4, one of them has 3. Whichever one has the least, that's how many your answer has. So I'm going to report my answer. What do you guys think how to report my answer? Yep, 7.23. Just for the sake of discussion here, I'm going to go ahead and put the whole number up here that my calculator said it was. That's interesting. 7.23456. Okay. So what you do is you're going to cut this off right here at 3 Sig Figs. And then you look at the first digit that's dropped. And well, what was the cutoff for running up and down? You remember what it was? Yeah, 5 and up, you round up. And less than 5, you round down. So I like to say if less than 5, round down. And once again, just to clarify here, I am referring to that number only. I don't care what's after that number, just the first digit dropped. And then if the number is greater than or equal to 5, round up. All right, so finally, to correctly report my answer, it is 7.23. And then if the answer was specified in scientific notation, you could add that little part there, but I'm not going to worry about that right here for now. All right, are there any questions about the multiplication and division rule? Go ahead.
I know you said you're not worried about it, but if you were writing that in scientific notation, would it be 7.23 times 10 to the 0?
Yes, it would be 10 to the 0. If you ever have a situation where you don't have to move the decimal, just put 10 to the 0. Yeah. It's good you asked that, because I have one of the practice quizzes online where it actually asks you to put everything in scientific notation. One of the answers is like that on there. So I like to do that in the first quiz for you guys, for funsies. All right, let's go ahead and just do one more calculation here. I'm going to add a few more operations in there just so we can see how the rules work. So let's say we have, 7.2, and we are going to cube that. And then we're going to multiply this by 1.23. And then we're going to divide that by, let's say 3.789. So looking at all the different operations here, if you're raising something to a power, you are technically doing multiplication. So if you ever have a calculation where you're raising something to a power, you want to go ahead and apply your multiplication rules. So here we are limited by Sig Figs here. So we have 2 Sig Figs in this number, 3 Sig Figs in that number, 4 Sig Figs in this number. Since all the same calculation is happening here, it looks like we're going to have, what do you think of the answer? 2 Sig Figs in our answer. The thing is, though, if you're doing a multi-step operation, you don't want to round before you're done calculating. So you want to just keep the number in your calculator, let it have that long string of digits after that. You want to round at the end. The reason why you want to round at the end is because if you round, every time you round, you add a little bit of error to your number in the calculation. So if you have someone, say you did like a 4-part calculation, one person rounded at each step and one person rounded at the end, there'll be about a 5% difference in the numbers. So you want to make sure you're not doing that. So sometimes if you're getting a slightly different answer than my answer keys, it might be because you rounded early. So I always round at the end. All right, so I want to go ahead and use this, and since you guys some of you are new to science classes, I want to illustrate how to use the calculator. So we have 7.2. Order of operations states that we should do this first. To use that, I have a little caret key. It looks like a little caret going up, and then you type the number. All right, and then times 1.23. I'm not a big fan of typing it all as one long string because if you make a mistake, you have to do the whole thing over again, typically. So that, and then we have the division step here, 3.789. All right, so there's my answer. So our answer should have 2 sig figs. So I am going to report my answer as 1.2 times 10 to the 2. So going back to this number here, basically I'm going to drop after the 2 there. And I put it into scientific notation just because it would have been 1, 2, 0. That last digit is kind of ambiguous. To make sure you're really clear about your sig figs, just put it into scientific notation. All right, and the rule that is not quite as straightforward is the one for addition and subtraction. This one's a little bit different. But for that, anybody have any questions about multiplication, division? All right. Alrighty, so the next rule I want to go over here, like I said, is addition and subtraction. These are opposite operations. The way this one works is that your result will have the same number of decimal places as the least accurate value. So result has the same number so now we're not talking about sig figs per se, we're saying decimal places. So same number of decimal places as the one with the least. Okay, so the way I like to do this, or I recommend doing this as you're first learning it, is when you're writing your numbers out, just go ahead and line them up by the decimal place. So suppose I had a number, so 12.347 plus 9.23. Let's go with that one. So I would go ahead and rewrite it to line up the decimals. So I'm going to put this over here. Lined up the decimals like that. At this point, you want to just go ahead and carry out the calculation like normal. Like, who adds by hand anymore, right? Guys remember how? Carry the 1 and all this stuff. Some people don't remember how to add by hand, which is kind of sad, but hope I got the number right after saying something like that. All right, so after you have your answer, what you do is you just cut it off here like that, and then you apply your rounding rules in the same fashion as we did for the multiplication and division. So it looks like here I'm going to have to round up. So I'm going to go ahead and write this as 21.58. You don't have to do this little step here, but I think it clearly illustrates what you're doing. You could just recognize, oh, that number only has 2 decimal places, so my answer is going to have 2 decimal places. You don't have to write all this out. It's just there for an aid if you need practice doing such. One issue that does come up with the addition and subtraction rule that students often get tripped up on is if you're changing your order of magnitude, because you may actually gain sig figs in some cases. So I want to do an example like that. So what if we had something like, let's say, 90.2, and let's go ahead and say it was plus, oh, let me get a bigger number here. Let's say it's 12.4. That'll work. Okay, you could set up the same way again. Just go ahead and line it up. 12.4. It looks like I'm going to get 1 decimal place, right? So what is the answer here? We have 6, 2, like that. So if you look at the original numbers involved, each of those only had 3 sig figs, right? But our answer to a correct number of sig figs has 4. And that's because it went up in order of magnitude. So these were all 10 to the 1, this went up to 10 to the 2. We still follow the same rule by the number of decimal places. So these each had 3 sig figs, the answer had 4. The most common time I see this type of issue come up is often with temperature conversions, typically when this kind of issue comes up. All right, the last thing I want to go over today for the last few minutes here is what do we do if we have multiple operations that involve like multiplication, division, and addition? Like how do we handle this? So if you have multiple operations, what you do is you follow the order of operations with that Pemdas, you guys remember that? And you apply the rules as you go along. You might be tempted here to do a early rounding kind of thing. Avoid any kind of early rounding. I think my camera just fully died at this point. It's not even showing on the screen anymore. Whatever. I'm hoping it's getting the audio. But I do want to get this up for you guys. In the case where I can't get this to work, I do have another video on there that does go over Sig Figs, so it is up there in some form. It might just be this actual lecture, it might be from last semester. All right, so calculations with multiple operations. So as I just said a moment ago, you want to follow the order of operations, which, if you recall, the acronym here was PEMDAS. And that stood for, what would that stand for? Parentheses, exponents, multiplication, division, addition, and subtraction. And you basically typically go left to right. So let's go ahead and just do an example. I think it's the best way to approach this. So let's say 3.14 plus